morning. In today's lecture we will be covering a lot of ground on the maximally decimated filter banks. We will look at the special case where m is equal to 2 channels, and it actually requires a fair amount of work to understand the mathematical analysis, how the filters behave, how do we design them, and how the whole system works together. So, but before that, there were a few questions after the lecture yesterday. So, I just thought I would clarify those doubts, so that in case those are broader doubts among the other students as well. So, just as a quick summary, whenever we do the DFT or IDFT, basically we view it as a transformation, but that is from a mathematical viewpoint or from an electrical engineering viewpoint, but from a signal processing viewpoint you think of it as some operation with filter banks. So basically you have a bank of filters which are shifted in terms of their center frequency, identical, shifted in terms of their center frequency, and this is a important element to keep in mind. And along with that, maybe an important aspect is that whenever we do spectral analysis using DFT, here are 2 points that always are worth remembering. The first one is that there is inherent spectral leakage. So, you can get some misleading interpretations, and it goes back to your filters not having just a passband, but they have got kind of ripples. So, therefore, you can get some erroneous conclusions. So, to improve upon this, we use windowing. Okay, so, without windowing, it is not a good idea to attempt the DFT. The second element that to keep in mind is that the number of the length of the FFT determines your spectral resolution. So, that is depends on the size of the DFT, and if you want to increase your spectral resolution, you should increase the size of your DFT. Okay. So, maybe the way to look at it is that we do a DFT operation, but there is an underlying filter bank function that is actually being carried out, and it is good to always link the fact that why spectral leakage occurs, how do I get more spectral resolution. Those are elements that you can obtain from the filter bank concept. Now, if I were to increase the size of n, what does it do to the filter bank size of the DFT? Increases the number of filters, makes them narrower. That is why spectral resolution goes up. So, okay, so that is where. Now, another important point to do or to keep in mind is that whenever we do the basic DFT, that is, you take a block of data and then you process it, there is implicit in your operation a rectangular window. Okay, so whether it was a finite length data or it was an infinite length data, the fact that you took a segment of length n effectively means that, so this is a default. Never forget that underlying any DFT operation, if you just take the DFT, yes, it is an orthogonal transform, but from a filtering point of view, you have windowed it and you have done that. Okay. Now, what happens if you use other windows? You get slightly better in terms of spectral leakage, but in all these cases your underlying spectral resolution depends on the length of the window or the length of the DFT as well. So, basically we are talking about a length n. The underlying filter has only length n. It can be a rectangular impulse response or a shaped impulse response, but the underlying length is n. Now, where does the filter bank come in? And a filter bank, on the other hand, is a special case of these windows. If you constrain the length of the filter to be equal to the size of the DFT, then it becomes that. So, filter bank actually allows you to have filter length arbitrary. It can be greater than n, and that is why a filter bank can reduce leakage and increase spectral resolution and give you the additional benefits. Okay, and this is any filter bank. but a special case of the filter bank is when you have a DFT filter bank. You have designed each of the filters as shifted versions. So, in that case you get a DFT filter bank, and whenever we want to compare it with the DFT, then the filter bank cannot be an arbitrary filter bank, it has to be a uniform filter bank, it has to be shifted versions, it would have to be very similar to what the basic DFT itself is doing. Okay. And if you have a DFT filter bank, then the added benefit is that if you now break it up into its polyphase components, then you get very efficient implementation, polyphase components. Okay. So, basically the polyphase components of your filter H naught of Z, if you were to label them as E naught of Z to E m minus 1 of Z, these are polynomials. The special case is when each of these is equal to a constant. This is equal to alpha naught E m minus 1 of Z is equal to alpha m minus 1, that is an arbitrary window, and if you take alpha naught equal to alpha 1 equal to alpha m minus 1, then you get the rectangular window. Okay. So, you see that the filter bank is the most general, you restrict the length to n, then it becomes a windowed filter bank, a windowed DFT. If you set all the window coefficients to be equal to 1, then you get your normal DFT. So, when you view it as a sequence of operations, then you get the insights and there is advantages to that. Okay. So, I will not repeat this, hopefully this is the a good enough reinforcement of what we have already covered. The other concept that we talked about is IFIR filter design, interpolated FIR filter design. So, the general structure is H of Z is equal to G of Z power L I of Z. Okay. Now, this can be used both for it can be used for upsampling and it can be used for downsampling. Both of them require filters, and IFIR technique is particularly advantageous if you have to have one of these. The key point to note is that this is where you get the sharp filters. This is what produces sharpness, but along with the sharpness it produces some unwanted images, and this is what removes the images. Okay. So, we take advantage of the fact that insertion of zeros compresses the spectrum, and then basically you need to take care of it by removing. So, this is the IFR technique is primarily used when you need filters with sharp transition, band, and it is definitely advantageous if you have sampling rate conversion as well. Even without sampling rate conversion, this may be an attractive method, particularly if you have sampling rate conversion, this would be the way to do it. And again, I do hope that if there is a need for you to design a sharp filter, you will keep this concept in mind. Okay. The next one, which we did spend some time yesterday, was the transmultiplexer, where we took 3 signals, upsampled them by a factor of 3, filtered them, and then produced the FDM signal. After the class, one of the students pointed out that at least few students pointed out that there was a mistake in the figure that I drew. So, let me just correct that figure so that that you will not have a confusion. So, this is the spectrum that we have drawn from 0 to 2 pi. And generally when we do the decimation or interpolation, it is good to keep in mind what it looks like from minus pi to pi, and I think that is where the mistake occurred. If you look at it from the point of view of the first branch produces 3 copies of the signal, and then I filter out the portion from minus pi by 3 to pi by 3. Okay. So, this portion is correct. So, from minus pi by 3 to pi by 3 you get a curved, from minus pi by 3 to 0 you get a curved portion, and then you get a straight portion. Now, this figure is wrong. Okay, what is the figure that actually should have been? If you look at it from minus pi to pi, the previous graph, let me draw it with a different color. Minus pi to pi actually looks like this, correct. So when I shift it, what I should have gotten was a spectrum like this, minus 2 pi by 3 to pi, and one more copy. And so this red line is not correct, the purple line is the one that is correct, and when you actually apply the filter, then what you pick off is this portion of the spectrum. So which means that the line will be looks like a V, not like an arrowhead. So this is the correct spectrum that you should have. And in the same way, if you go back and draw the third signal, then what you will find is that the third signal actually looks like this from minus pi to pi. So when copies are generated, then again it is of this type. This green line is wrong. What you should get here is again, okay, and therefore the correct spectrum is here. So this is again, make sure that you do note why this is the correct version, make sure you are able to get that. Basically the multiplexing operation does keep the copies, but the shape of the spectrum is equally important, so make sure that you preserve it correctly. Okay, we said that the inverse operation of the frequency division from translating from frequency division multiplexing to time division multiplexing can be shown to be the counterpart. Now there were a couple of questions with respect to how the OFDM and the filter bank are related, and whether there was some gap in what was presented in the class. I just wanted to make sure that we clarify that. So first let us just make sure that we are comfortable with this portion of it. OFDM, the transmitter, OFDM transmitter, again if there are any questions please feel free to raise it. There is a serial to parallel conversion followed by the IDFT, the dimensions are the same as the number of parallel lines, after which there is a parallel to serial conversion. Okay. Now the parallel to serial conversion is something that can be represented in terms of upsampling by a factor of m followed by a delay chain. This will basically reorder. If the vector came in as x0 x1 to xm minus 1, this would basically make it into a serial vector and present it to us. So this portion of the figure is clear. Okay, now what I would like to do is build on that so that we can link the two concepts that we have. Now ignore for the moment the second half. The first portion of is what we are interested in. This is the portion of interest. Okay, this is the transmultiplexing operation. Now this is the segment. If I were to draw a line around this block, this is where the copies of the spectrum are getting generated, am I right? So this is where the copies of the spectrum, as we saw in the 3-channel case, and this is the second part is where the filtering occurs to keep the correct copy of the spectrum. Depends on how you have designed the filters, you get a bank of filters, and this is the portion where we do the filtering and filtering the desired spectral copy. You keep the desired spectral copy, throw away the others. Okay. So I am sure that this part of it is you're comfortable with this being the setup that we have. Now what does the OFDM transmitter look like? I will spend a little bit of time just to make sure that this is clear. So there is an IDFT followed by upsampling followed by a delay chain. So if you do not mind, let us just draw that, because that is very helpful for us. Keeping this picture in mind, the picture portion of interest is starting from the IDFT. Again we want to show that there is a equivalence, and that's the idea of this discussion. And then the parallel to serial conversion, which then says there is an upsampling by a factor of m, upsampling by a factor of m dot dot dot. The last branch also undergoes upsampling by a factor of m, and then they are gathered together by means of a delay chain. Okay. There is a delay chain which gathers them together. Okay, and we get a sequence of data that has been presented to the inverse DFT. Yesterday we labeled them as S0, okay, S0, a symbol S0, symbol S1, a symbol SM-1. Now, just so that we are able to get the timing also correctly, please label them as n. So, at time index n equal to 0, you get a vector. Where did this vector come from? If you think of the S as a sequence of symbols starting from S0, S1 dot 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 SM, SM plus 1, your data you have split it into segments, and then you have mapped them into the QAM mapper. Then you take portions of them m vectors and then you block it. So, in the general case we get S0 of n, S1 of n, SM-1 of n, okay, and basically this would correspond to, if this corresponded to S of n, some index, this would have corresponded to S of n plus m. So, that would be the first vector and how it is formed. The second vector, basically we would label it as S0 of n plus 1, S1 of n plus 1, basically the next time index, SM-1 of n plus 1. So, that is this would correspond to, again it is a continuous stream of data. This would correspond to S, I think this would be n m minus 1, I am sorry. If you spot a mistake, please flag it so that we won't confuse everybody. So, this would be S of n plus m all the way to S of n plus 2m minus 1. Okay. So, basically the blocking occurs, I just wanted to make sure that you are comfortable with the notation. Yes, this is a continuous stream of symbols, but they are getting blocked into non-overlapping vectors, and then we obtain the result. Okay. Now, the first step that helps us in our analysis is that, am I allowed to move the upsampler to the left of the IDFT block? The answer is yes. Why? Because IDFT is an interconnection of adders and multipliers, and the upsampler can be moved to the left. Okay. So, please redraw this just so that we are comfortable with the sequence of steps. One more step. So, the first step, step 1 of proving the equivalence is to move the upsamplers. Upsampling by a factor of m, upsampling by a factor of m dot dot dot, upsampling by a factor of m, and no confusion as far as the data is concerned. This is the sequence S0 of n, this is the sequence S1 of n, this is the sequence SM-1 of n, and after this comes the IDFT. After this comes the IDFT, followed by the delay chain and the adder. Okay, we need 3 steps. This is the first step. The other 2 follow very easily from here. Okay. Okay, that is the output. So, the key element is now focus on this portion, focus on this portion. Okay. It looks a lot like the figure that we have drawn here. Basically, there is a sequence of upsamplers followed by a bank of filters. Now, the question that remains to be answered is this what is within the green box a bank of filters which is doing the same thing that what those filters are doing there for us. So, the key element is that what is what are the signals at this point? It would be S naught Z power m, right, upsampling. So, the signal at this point will be S m minus 1 Z power m. So, what we want is that this signal, if I call this as S of n, we want S of Z to be a filtered version of these upsampled signals. So, it should be F naught of Z, F 1 of Z, F m minus 1 of Z multiplied by the column vector where you get S naught of Z power m, S 1 Z power m dot 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 S m minus 1 Z power m. Okay. This is the transmultiplexing operation. Whatever signal comes in, you upsample it, that gives you the column vector, and then you combine it using appropriate filters. Okay. Everyone's comfortable with this? Basically what you will get is a scalar after this operation, and that is what is represented as the frequency division multiplexed signal. Okay. So, now we have S naught, S1, Sm minus 1. I just need to see whether these two are linked, and it is easy for us to do because the summation happens through a delay chain. So, that can be captured in the following form: 1 Z inverse Z minus 2 Z minus m minus 1, okay, and followed by the IDFT matrix, which I will denote as W star, W dagger. Okay. So, this is what is there in the figure. I have not done anything else. Now, that is step 2. Step 2 is when we have shown this. Now, I found it a little easier to try a specific example. Let me just highlight that. M equal to 4. In that case, I get 1 Z inverse Z minus 2 Z minus 3. Please look at this matrix: 1 1 1 1 1 W inverse W minus 2 W minus 3. In the case of W is actually e power minus j 2 pi over 4. Again, it does not really matter, but just your completeness. 1 W minus 2 W minus 4 W minus 6, 1 W minus 3 W minus 6 W minus 9. That is the W dagger matrix. Okay. So, from the previous comparison, F naught of Z is 1 plus Z inverse plus Z minus 2 plus Z minus 3. F1 of Z, the row vector times the second column, what you get is 1 plus ZW inverse ZW minus 2 plus ZW minus 3, which you can verify is the same as F naught of ZW, and this is the same as F naught e power j omega minus 2 pi over 4, basically shifted by the 2 pi over 4 center frequency. Similarly, you can do the rest. F2 of Z is F naught of ZW squared, and F3 of Z is F naught of ZW cubed. Okay. So, what did we say? F naught is 1 plus z inverse, that is our familiar filter bank. Where is my filter bank? Yes, 1 plus z inverse plus z minus 2, this one. The first next filter is shifted by zw, you get that. So, in other words, what is the OFDM transmitter doing? This block where you have the IDFT followed by the parallel to serial conversion can be represented as the DFT followed by the parallel to serial conversion. The upsamplers can be moved in front. If you move it to the front, then what you are left with the IDFT followed by the delay chain combination. What is the transfer function from each of these input points to the output? That is f naught of, I label that as f naught of z, because that is how the transmultiplexer diagram is defined, right. Output after the upsampler, the transfer function is f naught of z. So, what is my f naught of z? We have shown that it is a filter bank starting with a rectangular window and then shifted versions of it. So, basically what you are doing is, if you look at this operation, if you apply a vector to it, input to the IDFT block, so that means the vector gets operated on by the IDFT and then gets combined by means of the what will come out is a column vector, and that gets combined into a scalar using the delay chain, right. So, how do you get a scalar out of, so basically if you take it one more step. So, apply the input to this apply the input to this IDFT matrix. So, let us call this as S naught, S1, S2, S3. Okay. So, when you do the DFT, you will get a vector, column vector. If you multiply it by a row vector, which is 1 z inverse z minus 2 z minus 3, it is basically adding them with the appropriate delays, right. So, what we have shown here is an equivalent representation of what the block diagram is implementing. The S naught, S1, S2, S3, if that is your input to the IDFT computation is done, and then the summation is done through a delay chain. So, and now we are saying that, so what is the transfer function that is represented by this? So, by the way, this is z, do not get confused, you have to write this as z. I am trying to get the transfer function. Okay. So, basically that says that the f0, f1, f2, f3 are the, so in other words, so this is step 2. First step was moving the upsamplers, then analyzing the DFT. The second step was to show that each of these the combinations actually are. So, the final step is step 3 is to confirm the equivalence. So, in the general case, we get upsampling by a factor of m followed by f naught of z, okay, and upsampling by a factor of m followed by f1 of z. Okay. This is S naught of z, S1 of z, Sm minus 1 of z. Upsample by a factor of m, this is Fm minus 1 of z. In most transmultiplexers, the summation is not at the top, it is shown at the bottom. Okay, do not get confused, it is exactly the same thing, it does not matter at all, but there is a reason for this. Anytime a synthesis is happening, you kind of show that all the signals come and it gets sort of collected at the bottom. It is just a convention that is done. So, instead of keeping the summation at the top, and basically this is what is going to be fed to your channel, whatever your channel is. In this case, it will be a mobile fading channel to which you will transmit the signal. So, this effectively is your S of n, the combined signal, or if you want to represent it in terms of Z transform, this is S of Z. So, S of Z is f naught of Z times S naught of Z raised to the power m, f1 of Z times S1 Z raised to the power m dot 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 plus Fm minus 1 of Z Sm minus 1 of Z raised to the power m. Okay. Now, this is the general transmultiplexing operation where you convert into a frequency division multiplex signal. As you can see, this is where the copies are getting generated. Copies are getting generated. This is where the appropriate filtering is taking place. What we have shown that is that if you replace it with the OFDM type transmitter, IDFT followed by a parallel to serial conversion, that is the same as upsampling followed by the IDFT block, where the filters can now be represented in terms of the transfer functions that we just now shown. F naught of Z is 1 plus Z inverse plus Z power minus m minus 1, F1 of Z is equal to F naught of ZW dot dot dot. I won't repeat the rest of it. So, I hope this part of it is comfortable, and that is where we said that the OFDM is actually the transmitter portion of the OFDM is actually generating a frequency division multiplex signal, and it is beneficial for us to think of what those filters actually look like, and those filters are actually these filters, these shifted versions of these filters. And what is it that is being applied to these carriers? Those particular symbols, QAM symbols. So, each of these, and we said that you can do power allocation, you can choose not to use a particular channel if there is interference. So, lots of interesting things that you can do with OFDM. Again, those are things that you would have already seen in the communications course. What we are looking at is to give signal processing, and in particular a multirate DSP interpretation for the OFDM for the generation of the frequency division multiplex signal. In our terminology, it is a transmultiplexer, and OFDM actually is a transmultiplexer in the true definition of the word. Okay, any questions? Because there were several things which were questions were asked, and I was thinking we should probably make sure that this concept is clear. We will come back to study OFDM in its completeness. Right now, just to indicate that whatever we have developed is actually a very useful tool even in analyzing applications such as OFDM. Any questions? Okay. So, now we move on to the filter bank. So, we leave notice that there is a transposition that is happening in a transmultiplexer. What you have at the beginning, the first portion, this is the synthesis portion, and the second half is the analysis portion. Analysis is where the signal gets split, synthesis is where the signal gets combined. Okay. Now, the conventional multirate M channel filter bank is shown here. The analysis comes first, whatever processing you do, and then followed by the synthesis. Analysis, synthesis. So, again we see that the transmultiplexer operation is a transposition of the analysis and synthesis blocks. Most of the time when we are doing multirate filter banks, we are trying to split a signal. So, this is also linked, those of you who are familiar with speech, you have a technique called subband coding. Subband coding, where you say that you split the signal into different frequency bins, and whichever frequency bin has got more information, you use more bits to encode that information, right. So, for example, you split it into high frequency and low frequency, you find that the low frequency has got more information, so you use more bits to indicate the low frequencies than the high frequency. So, therefore, you get a form of compression. So, the whole filter bank theory came from its applications in subband coding. Subband coding has been used extensively in speech and in image, and continues to be used in these applications. So, this is a very foundational block that we are looking at, and in this context what you have is a composite signal, basically the speech signal. You split it into different frequency bands and then do the processing, and then at the other end, so this may not happen at the same end, you may have a transmission happening in the middle. For example, this could be a transmission that is happening, and at the other end you will do the reconstruction. Okay, so this is a very general framework, very important framework, and useful framework as well.